Do black holes really smash together? Yep. Here is how scientists mapped out one collision in real time and what we can expect from future detections. This is our channel. At first glance, this might look like your typical grainy black and white surveillance footage. But if you look closely, you can see that the frame is slowly stretching and distorting as something weird happens to the clock on the wall. The desk is moving, but the cabinet in the background isn't. Then you notice the creeping shadows and realize that the entire room itself is what's actually moving. You turn just in time to see yourself running away as the walls close in around you. Wait, where are you going? What are you running from? And most importantly, why does it all look like that? Is this some kind of cryptic message from our overlords at the start of an episode of The Twilight Zone? Well, yes, it sort of is. You're seeing a simulation of gravitational waves. These ripples in spacetime were predicted by Einstein more than 100 years ago, but it wasn't until 2015 that they were finally detected for the first time. That was a monumental moment because it opened up an entirely new way of exploring the cosmos. It's called Gravitational-Wave Astronomy. And while it's still in its infancy, it's already taught us some surprising things about the universe. Take last year's detection of a gravitational wave event called This one had a lot of scientists scratching their heads because its source remained a total mystery. No telescopes on Earth or in space could see what was out there, at least not right away. But with some clever work, astronomers have now solved the case and revealed that the culprit was a pair of neutron stars. In this animation, you can see two neutron stars orbiting each other. Every time they go around, they emit gravitational waves which carry energy away from the system. As a result, they spiral inwards towards each other, getting closer and closer with each orbit until, bam, they collide and merge into a single object. If you were standing nearby, you wouldn't hear a thing. The sound waves would be completely silent. But thanks to LIGO, we were able to hear the echo of this cosmic crash course all the way here on Earth. The Laser Interferometer Gravitational Wave Observatory consists of two separate detectors. They're located thousands of kilometers apart to help pinpoint where these signals come from. Both detectors are shaped like L's and are 4 kilometers long. At each end of the arms is a mirror. Laser beams shoot down them, bounce off the mirrors, and then recombine. When a gravitational wave passes through, it stretches space, altering the length of one arm relative to the other. This changes the phase of the light waves, which is measured by a photodetector. It's worth pointing out that these detectors are so sensitive that if you wanted to measure the distance between the Earth and the Moon with them, you'd only need half a picometer. To put that into context, if you were to stack up 3.3 billion of those picometers on top of each other, they'd reach roughly the height of Mount Everest. So it's fair to say that these instruments are pretty dang precise. But despite their sensitivity, they can only detect the largest gravitational waves. To see the smaller ones, we need to improve the precision of the measurements we can take. And that's where the LISA LAVOI, or Laser Interferometer Space Antenna, comes in. LISA will consist of 2 spacecraft flying in formation across the solar system. Its arms will be 2.5 million kilometers long, equivalent to the distance between Earth and the Sun. Thanks to this large scale, LISA will be able to observe gravitational waves that are 10 to 100 times smaller than those LIGO can currently detect. That might not sound like much, but it means that instead of detecting just a few dozen events per year, we could be detecting up to 10,000 mergers. In fact, it could even be possible to detect individual stars collapsing into black holes. With that many observations, we'll be able to study gravitational waves almost like we study electromagnetic radiation. We'll be listening to the light, so to speak. So let's get back to Capella. The gravitational wave signal was first detected in February 2020. All they knew initially was that the source was around 800 light years away and that it released about 3 times more energy than the previous event. After that, everything was up in the air. There was a wide range of possible sources. It could have been 2 black holes, 2 neutron stars, or even a black hole and a neutron star. The latter would have been particularly interesting because their mergers produce a huge amount of heavy element. It's thought that most of the gold, platinum, and uranium in our own solar system came from these cataclysmic collisions. And unlike regular stars, which shine by nuclear fusion, these objects shine by nuclear decay. We call them so if the merger was a kilonova, we should be able to see a bright flash at the same location when astronomers pointed their telescopes skyward. But at first they saw nothing. It looked like the kilonova had been absorbed by the dust and gas in our galaxy. Now, while astronomers were able to identify the rough location of the source, exactly where it was in that region was totally unknown. They needed some way of narrowing it down. And of the all-sky medium-energy gamma-ray explorer, or SWIFT, this telescope searches the skies for gamma rays, X-rays, and ultraviolet light. Its primary mission is to find the sources of short gamma-ray bursts, which are intense emissions of gamma rays from distant galaxies, but it's also helped search for several known gravitational wave sources. When the burst from Capella was detected, SWIFT was able to localize it to a region of space less than 2% of the size of the full moon. Then, a team from the Dark Energy Survey Supernova Collaboration got involved. They've been surveying the universe in search of supernova, which are the explosions that occur at the end of a star's life. Their survey has found hundreds of these stellar deaths, and in 2017, they published a paper outlining their search for supernova in the Milky Way. They were able to identify one that happened just a few hundred light years away. So when they heard about Capella, they realized they could search nearby to see if there were any records of a supernova. They looked back at images taken a year before the gravitational wave detection, and sure enough, they saw a faint dot that wasn't there before. They couldn't confirm it was a supernova after all, without repeated observations. You don't know whether you're looking at a new star or a background galaxy. But they could say with 95% certainty that whatever it was, it had exploded within 100 light years. This was the breakthrough they needed because it narrowed the search down to a small group of stars. It didn't take long to find the culprit. A few months later, the source was identified as a binary system containing a neutron star and a black hole. Now this makes Capella the most nearby gravitational wave source ever discovered. The detection also solved another mystery. After the original gravitational wave detection was announced, researchers noted that there seemed to be a second signal buried in the noise. They weren't sure if it was a glitch or not, and even if it was real, it could have come from anywhere in the sky. But by pinpointing the source, the team could also look for this secondary signal. They found that it was real, and it came from the same place, meaning that what they originally thought was one source was actually two. Researchers are excited because it shows that even with relatively small detectors like LEAP, we can find multiple sources in one signal if we can narrow down the location. The next generation of ground-based detectors, like the Einstein telescope or the Cosmic Explorer, will be bigger and even more sensitive. It's feasible that they'll be able to detect 100 mergers in one shot. By observing them all, we'll be able to better understand which type of merger produces which type of afterglow, and by comparing the light with the gravitational waves, we can test Einstein's general theory of relativity to ever greater precision. But if we want to detect smaller signals, we need to venture beyond Earth. We can use the atomic clocks on satellites to detect gravitational waves passing through space. This idea is currently being tested by the LISA Pathfinder mission. Once fully deployed, the LISA Observatory should be operational by the early 2030s. The best part is that with these new observatories, we'll be able to observe gravitational waves in other parts of the electromagnetic spectrum. By combining the data from multiple wavelengths, we'll be able to image the mergers in 3 dimensions. It'll be like watching a movie. And it's not just black and white either. We'll be able to see the pops of color as elements are forged and thrown out into the universe. With the passage of time, our ability to detect gravitational waves will only get better. And each time we do, we'll learn more about the structure of our universe. Who knows? Maybe one day soon we'll be able to hear the whispers of the Big Bang itself. Thanks for watching this episode, which was brought to you with the help of our patrons. If you'd like to help us make more videos like this, you can get started at our support page. Also, don't forget to subscribe so you don't miss our next upload.